Howdy, today on Flippin Science we're talking about molecules, ions and octet expansion. So the first set of learnings we're going to look at are predict whether or not a compound or element is molecular given its properties, name, elemental composition or formula. So where do you get molecular substances from? We'd normally say that small molecules consist of 10 or less atoms per molecule, and we call these molecular substances. And they can be compounds or elements. It just depends on what elements are making them up. The general group that we're looking at in terms of the elements that are going to form molecules are these ones over here, and as well as hydrogen up in the top left. So things like oxygen gas, O2, that's a small molecule. Water, H2O, that's a small molecule, that would be molecular as well. Other elements like nitrogen gas, for example. So there's many molecular compounds you can make using just these elements from this side and this side over here. So let's have a look at some molecular and non-molecular substances. So I said already oxygen gas, chlorine gas, carbon dioxide. So if we have a look down here, we've got chlorine over here, oxygen here, carbon dioxide over here. They're all non-metals bound together, and they use covalent bonds to do that. We looked at magnesium oxide. That's not molecular because it's made up of a metal and a non-metal, so that would be an ionic solid. So it would be a big 3D lattice of positive and negative ions attracting each other through electrostatic attraction. Water is molecular, so water is down here, H2O, because it's not, hydrogen isn't a metal, so it's non-metals bound together with covalent bonds making small molecules. Sometimes you can get non-metal compounds that are not molecular. Silicon dioxide, for example, is made up of silicon and oxygen atoms covalently bound to each other and making a large 3D lattice. Similarly, diamond, which we have a picture of here. Diamond is very similar. It produces a large 3D lattice, and it's bound with lots of covalent bonds joining the atoms together. So it's not small molecules, it's large 3D lattices. So that's why they're not molecular. So let's talk about some properties of molecular elements and compounds. Generally speaking, they have low melting and boiling points, so usually liquids or gases at room temperature. That's because there's very weak secondary bonding usually acting between the molecules, and when we're talking about melting and boiling point, we're talking about the secondary interactions between the molecules if we're talking about covalent substances. So because they have a very weak bonding between the molecules, they have low melting and boiling points. Some other factors are they're poor conductors of electricity in solid, liquid and gaseous state, because they don't have any free charged particles that are readily available to move around. If you want to conduct electricity, you need to have charged particles that are free to move under the influence of a potential difference. And there are no charged particles floating around in pure molecular elements or compounds. So the question is, why do you get electrocuted in water? Water is a molecular substance. It shouldn't conduct electricity. And the reason why you get electrocuted is the water itself doesn't conduct electricity, but the ions that you often have in salts that dissolve in water do. So salt water conducts electricity really well. The water allows the ions from the salt to move around under the influence of a potential difference. So that's why you can get electrocuted in water. The second set of intended student learning is we're looking at drawing diagrams of molecules again. This time we're going to look at particularly elements, so we're focusing on the two element ions containing no more than 5 atoms. And we're also going to look at octet expansion and the molecules that you have to draw there. There's only 3 molecules that you have to draw showing octet expansion, so phosphate ion, sulfur dioxide and sulfur trioxide. So I'm going to show you how to do that. We're going to start by drawing some ions. So we're going to start with the ammonium ion. So this is one that you should be able to draw because it's a 2-element ion up to a total number of 5 atoms. The way to look at it is the nitrogen in the middle is it's lost an electron, so it has 1 fewer electrons in its valence shell than it normally would have. And because of that, it's making an extra bond, so it makes an extra bond with an extra hydrogen. So that means the nitrogen is acting like a carbon, and that gives you a good idea about what the shape is going to be. So we're going to follow our steps for drawing molecules that we learnt about before. So step 1, which our atom has the highest covalence, our nitrogen is going to be 4 in total because it's lost an electron, so it needs to make an extra bond. Hydrogen is going to be 1, so we're going to put nitrogen in the middle. And step 2, so we're going to put the other atoms around it in a symmetrical way. Next step, we're going to draw in the bonds that satisfy the covalence of each of the atoms that we're looking at. So each hydrogen needs 1, the nitrogen needs a total of 4 now because it lost that electron in the middle. And then we need to distribute any non-bonding pairs and then do the electron pairs symmetrically around it. So we've got 4 bonds, so in 3-dimensional space that's going to form a tetrahedron. So the last step is we're going to indicate the charge, and there's 2 ways of indicating the charge. One way is using square brackets like this, and then putting the charge on the outside of the square brackets. So here we've got the positive charge on ammonium. The other way is to place the positive charge on the atom that has the positive charge. So to do this, I'm going to go over here. So I've got my nitrogen. I'm going to put my hydrogens in, symmetrically around it, tetrahedral structure. And then I'm going to put my charge, and the charge for this one is on the nitrogen atom in the middle. It's not on any of the particular hydrogen atoms around the outside. The positive charge is in the middle on the nitrogen atom. Now the next bit we need to look at is octet expansion, because that leads into the drawing the molecules that have expanded their octet. So phosphorus, chlorine, sulfur and other elements as well can expand their octet. What that means is rather than just filling up their valence shell until they get a full valence shell, what they can do is reconfigure their electrons so that they can get more bonds by using a larger valence shell, a valence shell of higher energy. So let's have a look at the electron configuration of phosphorus. So it's number 15, so 1s2, 2s2, 2p6, 3s2, 3p15, so 3p3. So we'll talk about phosphorus in a second, but the way that you expand the octet of phosphorus is you can take these 5 electrons here, so the 2 here and the 3 here, and put them into the 3d subshell. That way, rather than only forming the 3 bonds that phosphorus would normally form to fill up the 3p subshell here, you can get 5 bonds by sharing 5 electrons from the 3d subshell, and we'll look at that in a minute. We look at sulfur, so we've got sulfur 16, 1s2, 2s2, 2p6, 3s2, 3p4. Now, sulfur can do a lot of things. It can move, say, 5 electrons, so leave 1 in the 3s, and move all 4 and that one into the 3d, so it can make 5 bonds that way. It can also make a total of 12 bonds by removing that one and I think putting it somewhere else. So there's lots of options for octet expansion. Let's look at phosphorus in a bit more detail. So if we have a look at phosphorus, we can look at how a compound like PCl5, so phosphorus pentachloride, can exist. So what it does is it moves its electrons from the 3s and the 3p, and instead it half fills the 3d subshell. Okay, and now it can form 5 bonds because it can get an electron coming in here, 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 and here. So if we look at phosphorus pentachloride down the bottom, by sharing 1 electron with each of the 5 chlorines that comes in, we can get 5 bonds rather than the typical 3 bonds that phosphorus would make. So that's an example of how octet expansion would work. So now we're going to look at the phosphate ion, PO43-. So what's happened with the PO43- is it's expanded octet by including an extra electron pair. 3 of the oxygens have a negative charge and 1 has a double bond with the phosphorus. So let's follow our steps to figure out what the shape would be. So again, step 1, find the highest covalence. It's going to be phosphorus. It's going to try making 5 bonds in this case. Place the atom highest covalence in the middle, and then the oxygens with a lower covalence of 1. So that's 1 for 3 of the atoms, since they have a charge of -1 each, and then a double bond for the third one. So now we're drawing in the number of bonds to satisfy all the requirements of the covalence. So this one needed 2 bonds, this one needed 1, 1, 1. I haven't put the charges on, we'll put that on shortly. We need to make this symmetrical, so again in this case, here we've got it flat as if it was 2-dimensional. Remember, in 3-dimensional space, this would be a tetrahedron. If we look at where the repulsion is going to be, we can pretty much ignore all the outside ones. We're looking at these ones down here, so we're going to get tetrahedral arrangement of atoms around the phosphorus there. So here I'm showing the tetrahedral shape, so we can see that we have 4 things repelling around the central atom, which gives us a tetrahedral space. The last bit is we need to indicate the charge. So the charge on this is -3, since we've got the extra electron for each of the oxygens out here. So PO43-. Again, the other way we could write this is by putting our phosphorus, oxygen, 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 and then putting the negative charge on each of those oxygens down there. That's the other way of writing how this would look. I think this one looks cleaner, so that's the one that I would go for. The only other two molecules you have to draw that are expanding their octet are sulfur dioxide and sulfur trioxide, so let's look at those now. So we've got sulfur in the middle, that's going to be our one with the highest covalence, it's forming the most bonds. For sulfur dioxide, it's got a double bond for the two oxygens that are coming in, and it has a non-bonding pair of electrons at the top. So the total number of electron pairs is 5. So 1, 2, 3, 4, 5. So it's got 5 electron pairs. These two count as 1, that counts as 1, so we get a V-shaped molecule, a bent molecule there. We look at sulfur trioxide, we've got to have 3 oxygens in there. Again, the sulfur's in the middle. The sulfur's expanded its octet, and now it can form 6 bonds. So we've got 1, 2, 3, 4, 5, 6 bonds. So we've got 3 oxygens with 6 bonds. This is going to be a trigonal planar molecule. So today on Flipping Science we looked at molecular substances and their properties. We looked at how to draw ions and also how to deal with octet expansion. That's it for Flipping Science today. See ya.